Yeah, yeah. Thank you for giving me this opportunity. I am Dr. Handevam Baru Sharma, sports and exercise medicine specialist, clinical and medical physiologist, and I am the president of Indian Society of Sports and Exercise Medicine. Let's begin the talk. So before going to detail of the sports nutrition, one has to understand the sports and exercise medicine as a specialty. The ultimate aim is CITES, Altius, broad sports, exercise, and human performance, and another is the medical, clinical, allied health science. And these are the different subsection of sports and exercise medicine. And one of the subsection is performance enhancement by training, nutrition, psychology, and other scientific intervention. So sports and exercise nutrition is a very much part of sports and exercise medicine. So concept of sports and exercise nutrition. One is the classical high carb approach, another is a low carb approach, and this is the high carb approach where carbohydrate from the base of the pyramid, whereas the high fat approach where fat from the base of the pyramid. And there are conflicting evidence, which one is better for what, because if we have to focus on performance as well as term health also. And there are lots of available evidence one has to look. So one has to keep their mind open and readily accept the evidence-based approach, even if it is challenging your belief. So belief is not important, evidence is more important. And before going into the detail, we must understand the basic physiology in the form of the muscle bioenergetic. These are the different form of bioenergetic already known. Phosphating system up to 15 seconds, it can provide anaerobic glycolytic system 2 minutes, oxidative phosphorylation system more than 2 minutes. There are different form, and these are the different concept of the energy production. Like for example, 1 gram of carbohydrate can produce up to 4.1 kilocalorie. It's same as protein. For fat, it is 9.4. That is fat provide more energy. Fat provide more energy, but if you see the energy production in terms of the oxygen, like for example, 1 liter of oxygen, carbohydrate provide more energy as compared to fat. If you see per molecule, carbohydrate provide more energy as compared to fat. Also, if you see the amount of the ATP production per second, that is rate of the ATP production, carbohydrate provide more compared to the fat. Like for example, fat oxidative, it provide 1.5 ATP per second. For carbohydrate, in case of the glycolysis, anaerobic glycolysis, they provide up to 5. For oxidative phosphorylation of the carbohydrate, they provide up to 2.5. So carbohydrate can provide which is strain base, anaerobic base, sprint type. So this is the classic teaching. But what does the evidence says? This also one has to understand. And what about the amount of the energy present in our body in the form of fat or carbohydrate? This carbohydrate is liver and muscle glycogen. This is the subcutaneous fat and intramuscular fat, and this is adipose tissue. You can see that as compared to the amount of the muscle and liver glycogen energy, the amount of the fat is huge. That means the fat can provide the energy of approximately 4 days of running as compared to 2 hours or 40 by muscle and liver glycogen. So if you are able to utilize fat, selectively fat more effectively, then your endurance performance will be much higher. You will be able to run for a longer time, if you use more fat. But if you use muscle glycogen, then you may need replenishment after say 2 hours or so, because they have a limited storage. So this thing one has to understand. There are benefit, there are the disadvantage of the carbohydrate. Point of the oil utilization is a crossover point after say 65. The exercise beyond 65 point, the amount of the contribution from the fat is decreases as compared to the carbohydrate, which keep on increasing. That means the fat has a maximum oxidation point around say a point 2 to 0.6 or 0.3 to 0.6 per minute. That is the maximum. This is known as fat max zone. And if you extrapolate this graph, you can say around 85 or more percent of contribution of the fat may be zero. So this is the problematic. For exercise at a very high intensity. That is the problem. But some of the athletes, some of the authors, they have argued that yes, the acid present, hyperemia will happen, and which will lead to the exhale out of the more VCO2, that is volume of carbon dioxide, which will increase RER. And this increase in RER can be misinterpreted as contribution from carbohydrate, because more RER means more utilization of the carbohydrate, less RER means more utilization of the fat. Of the hyperemia, because of the high hydrogen ion, may be misrepresented, and hence underestimation of fat oxidation may happen. So this one has to understand what is the proof. There are lots of studies which has shown that in case of the low carb diet athlete, the contribution of the fat is much higher as compared to the high carb athlete. Like energy expenditure is much higher from the fat in case of the high carb low fat athlete as compared to the mixed athlete. And one has to see that this crossover point is much higher in case of the low carb high fat athlete. It is more than 80% of VO2 max. In case of the normal individual, normal means high carb, athlete, it is around 65 or so. And the fat max zone for a normal, high carb athlete is around maximum up to 0.6 gram per minute or so. But in case of the high carb per minute, that means your body is able to utilize fat at a very high rate even, and at such a very high rate, theoretically you will be able to perform high intensity exercise also. That means in case of the highly fat adapted athlete, he or she may able to use fat for high intensity exercise also, for anaerobic just like anaerobic exercise, what the carbohydrate is serving. So that is the point. Another point is for we have already seen that around 85 or so of VO2 max, the contribution of fat is minimum. But in case of such athlete, high carb, low fat athlete, the amount of the fat oxidation even more than 85% of VO2 is very high. Like for example, 1.5, 1.58 plus minus 0.33 gram, even achieving more than 1.85 gram per minute of fat oxidation, very high rate of fat oxidation. That is also at 86.4 plus minus 6.2% of VO2 max, very high intensity of exercise. That is at higher intensity of exercise, you are able to utilize fat at a very high rate. That means you are able to perform high intensity exercise by utilizing fat also. The fat is utilized not only for endurance, but also for different type of exercise. So by adapting to the low carb, high fat diet, you will be or theoretically able to perform lots of different type of exercise. This one has to understand. So this is the different paper which reported different fat oxidation. Like for example, this is the Burke et al. They approximately around 1.5 gram per minute of fat oxidation. And similarly in this paper, you can see this is the pre and a post. Yellow is the pre, blue is the post. This is the carbohydrate oxidation. This is the fat oxidation. Low carb athlete after adaptation to the low carb athlete, the fat utilization as a higher rate will increase though. So that's why theoretically we have in the first slide we have seen that the limitation of fat is, although fat more, the rate of ATP production for fat is lower. This is what the classic teaching shows. But recent evidence shows that the rate of fat oxidation is very high. It may be similar to carbohydrate. It may be little lower than carbohydrate, but or it may be similar to carbohydrate, and hence theoretically the fat energy from the fat may be able to provide energy from different type of exercise, including the high intensity exercise. This one has to understand. And for fat adaptation, it may take long time. It may be more than 3 to 4 weeks, or say 3 to 6 months or so. And during the fat adaptation, there may be some adverse effect can be seen. Performance impairment can happen, and that's why it has to be. What about the we will be focusing a little bit. And since the classic concept is focused on carbohydrate, 60 to 70% of the carbohydrate, and these are the different concept, like for example, low GI diet is given, 1 to 4 gram per kg 2 to 3 hours before the event, or high glycemic index is avoided 15 to 45 minutes before the event. Otherwise, hypoglycemia can happen because of high insulin, high GI diet, high glycemic diet. After the post event or recovery can be given for glycogen replenishment. Protein plus carbohydrate is used 1 to 1.2 gram per kg per hour up to 4 hours. We generally use for moderate intensity, moderate duration, low intensity, 5 to 7 gram per kg per day, or up to 12 gram or more per kg per day of extreme exercise, 4 to 6 hours, but can be used. These are different things which are being utilized. And similarly for sports drink also, 4 to 8% of carbohydrate in the form of glucose, fructose, or sucrose. If you want to add more, then in a combination of glucose and fructose is added in the form of sucrose in a ratio 1:1 or 2:1 or 0.8:1, on depending with different, say, sodium, potassium, chloride, magnesium, all these things. But you should avoid over drinking, because dilution and hypernatremia can happen, which is a fatal condition. These are the from where this evidence come of utilizing high carbohydrate. This come from the classic experiment done by different authors. Like, for example, during 1971, this has been done during 1967. Here you can see that this is the muscle glycogen, this is the exercise performance. You can see that those athletes who are having lower muscle glycogen, they are able to perform, they are able to exercise for a shorter duration. That means having higher muscle glycogen means longer exercise capacity. So this was interpreted by the author as saying that the muscle glycogen is more important for exercise performance. That's why they have drawn this linear graph where this is the initial muscle glycogen, this is the exercise endurance time, and there's a linear relationship, that is having more muscle glycogen means more performance. But they have forgotten to look at this graph. You see there is another graph where blood glucose is there. Those who are having lower muscle glycogen, they are having low level also. So this performance impairment may be because of the low blood glucose. You never know whether it's because of the muscle glycogen or blood glucose. One has to understand. But they have neglected blood glucose level. They have focused only on the muscle glycogen, and based upon that, they have recommended different recommendeds are given. Like, for example, here in this, you can see that this is the carb loading. Carb loading is basically done in order to increase the muscle glycogen level. It also increase the liver glycogen, and you can see that the carb loading athlete has a more performance. They are able to perform quickly as compared to the mix, and this is the amount of the glycogen. Here you can see that the much glycogen is there. So glycogen loading has been taken as a technique in order to improve the performance, and hence different recommendation are there. Like, for example, 8 to 12 gram per kg per day of carbohydrate can be taken 3 to 4 or 7 days of tapering, plus 70 to 80% of carbohydrate intake can be taken, or recovery 1.2 gram per kg per hour in first 2 hour, or pre-exercise 1 to 4 gram per kg of body mass 3 to 4 hours before the excess of the glucose intake. Glucose polymer can be taken if the excess is more than 2.5, or then 90 up to 90 gram per hour of glucose or fructose blend can be given. This is the rate of the utilization. So all these things are based upon this. But what about this glucose, blood glucose? This one has to understand. And again, similarly, there are lots of recommendation. It may be whether 30 gram per hour, 60 gram, 90 gram per hour, depending upon, say, 3 hours or 2 hours or 60 minutes, or if the event is less than 60 minutes or so, 30 minutes, around 30 minutes, then small amount of mouth only rinsed with carbohydrate can be done. In fact, very high. Some athlete has taken, the maximum your carbohydrate oxidation is 100 gram per hour, adding 20 gram in order to compensate the loss. So 120 per hour given, and they have shown that this athlete has a lower rating of perceived exertion, and lower marker of the muscle damage. All these things is given. That means high intake of carbohydrate up to 120 gram per hour has been prescribed by different paper. But the point which I want to make is, is it really necessary to give such a large amount of carbohydrate? Because on the other hand, lots of paper has been there, which shows that the intake of high carb diet, for a very long time will lead to insulin resistance and metabolic abnormality, obesity, and all this thing. And athlete, we are giving such a high amount of carbohydrate. This one has to understand. And also regarding the ratio, one has to see whether glucose and fructose ratio, whether you give 90 gram per hour or 120 gram per hour, the ratio may 2 is to 1, 1 is to 1, 0.8 is to 1, 1 is to 1 is the sucrose solution. Of the exercise, more than 3 hours of exercise, 2 hours of exercise, 1 hour, depending upon that, optimum ratio you have to design, because there is no optimum ratio. You have to design yourself. So all this thing is important. But the answer again remains the same. The question remains the same, whether muscle glycogen is important or blood glucose is important. Because if the muscle glycogen is important, then whatever we are doing is correct. But if blood glucose is important, more important than loading of carbohydrate before all this thing is not necessarily. Let's see. So this is the graph. This is the paper. You can see that this is the blue line is a placebo. There is no intake of the glucose. This is the intake of the glucose polymer, and you can see that this is the carbohydrate oxidation. The muscle glycogen keep on falling, and here they are same for what? Same for whether you take glucose during the exercise or not. Muscle glycogen is same, but in spite of the having same muscle glycogen, at a low muscle glycogen, the person who are taking glucose polymer are able to exercise more longer. That means intake of the glucose is more important than having muscle glycogen, because they are same. This those person who are not taking this glucose polymer, here, they stop the exercise here. And in spite of having same muscle glycogen, this person is able to do it. That is, muscle glycogen is not so important. And again, different paper have shown that in spite of the decrease in muscle glycogen, the amount of the ATP remains the same. That is, ATP is required for muscle contraction, muscle relaxation. So the muscle glycogen doesn't have any effect on the ATP, as well as the TCA cycle intermediate. That means the biochemical process is going on, whether your muscle glycogen falls or not. So decrease in muscle glycogen is not the absolute determinant for exercise performance. This one has to understand. And also, when you give carbohydrate before, and this is the placebo, that is before carbohydrate loading or not, whether you load carbohydrate or not for 4 kilometer or 1 kilometer sprint, in case of the time or power, doesn't matter, because statistically they are not so different. That means there is no benefit of the carb loading when carbohydrate ingestion is done during the exercise. So as long as you are taking sufficient carbohydrate during the exercise, there is no need of the carb loading by this paper you have this paper has shown. So what is the theoretical basis? The theoretical basis, you have to see that as exercise duration prolonged, muscle glycogen falls, but ATP has to be provided because exercise is going on. This ATP is provided by alternative fuel, like for example muscle triglyceride or a blood-bound substance like free fatty acid, glucose, lactate, ketone. But after some time, if you keep on doing the exercise, then ultimately this alternative fuel source will also not be able to provide ATP. Then there will be some ATP deficit. But your basic knowledge of physiology tell you that if ATP is not there, then muscle relaxation will not happen. So what will happen? Muscle rigor will happen, just like in rigor mortis, but it doesn't happen during the exercise. Fatigue happen before the muscle rigor develop. That means something must be there in order to prevent the happening of the muscle rigor, and that something is nothing but the central governance. Just before this deficit develop, and this requirement of ATP can only be developed, can only be produced if you stop exercising, if you decrease exercising. So in order to protect the homeostasis, motor unit recruitment in exercising limb in anticipation is reduced by your central governance theory. That is important. And how this can be proven? This can be proven in the form of the fatigue. So if you see, if you keep on doing the exercise, then after some time, your fatigue will be linearly increased and your fatigue will be very, very high. And if the fatigue is more than 18.1 or so, if the ARIA, there is a irrespective of whether you have high glycogen or low glycogen, doesn't matter. In both the case, the fatigue is linearly related. And again, here you can see this is the power output. When fatigue says the power output decreases because of the fatigue. And here you can see the EMG. The EMG also decreases. That means recruitment of the muscle fiber also decreases. And this decrease in muscle fiber is because of this decrease in recruitment of muscle fiber is because of your central nervous system. Your central nervous system is catastrophic, health abnormality because of the, it may be complete ATP depletion or some heat problem, heat stroke, and in order to save the body. So this is the central governance theory. Another, evidence which point to the existence of the central governance theory is this paper. You can see that if you keep on doing exercise without taking carbohydrate, then your blood sugar will decrease. This is the decreased blood sugar. And because of the decreased blood sugar, your glucose uptake by your brain will decrease suddenly. This is the glucose A minus B glucose uptake difference. That is glucose uptake by your brain. It is sufficiently decreased after say 120. After 120, you get blue line. It suddenly decrease, and blue line is the one without any glucose uptake. And because of the decreased blood glucose level, the glucose uptake by your brain decrease, and because of the uptake of at 120 glucose level is important, because this maintenance will keep on providing the glucose of the brain, and hence rating of perceived exertion will not be there. So exercise induced hypoglycemia is very important. You have to prevent it. And this is the central governance theory. Central governance, your and all, they will perceive the the fuel availability, and based upon that the motor recruitment whether, because see, contraction of the muscle is the degree of the motor unit recruitment in exercising muscle by the motor cortex is a major determinant of rate of the blood glucose uptake during the exercise. Less blood glucose is present, the brain will feel threatened, because the brain doesn't have any storage for glucose, unlike the muscle or glycogen, muscle or liver. And therefore, if the brain feel threatened that the source of the glucose is keep on falling, then the brain will shut down the muscle recruitment, muscle by using the nervous system, and hence you will not be able to do the exercise. So this is a central governance theory. And therefore you have to prevent the hypoglycemia. Liver glycogen is more important, because liver glycogen contains the glucose phosphatase. It can directly produce glucose and contribute to the blood glucose level, but muscle glycogen doesn't do that. Muscle glycogen is not so important. Liver glycogen is more important. And fat oxidation and ketone body, if you are able to use more ketone body, then your brain and your muscle will be able to rely on alternative fuel source apart from glucose, and glucose can be preserved for later use. The glucose sparing effect is there. So fat adaptation is more useful. Your brain will be able to use the ketone instead of glucose delayed. And therefore, in order to prevent, if a carbohydrate is not ingested, then in order to prevent all these things, your brain reduced insulin will be reduced, a restrained amount of walking will be there, you will not be able to walk. And if fail, then athlete may collapse in order to prevent the brain damage. So this is basically the central governance theory. And 25 gram of the glucose, that is 1 teaspoon of the glucose, and this maintenance is important. And diagram, this is a different pattern, that is high glycogen plus intake of the glucose, high glycogen without intake, low glycogen with intake. Low glycogen means the person who is following a low carb diet. Low carb diet plus intake of the glucose. See, if you can see that here, it is green and the red line. This is the green line and red line. Approximately same power of it. That means even if you follow the low carb diet, but if you take glucose during the exercise, then the fatigue, the power output is similar to those who are following you are following without intake of the glucose, then your blood glucose level for is maximum. If you take adequate amount of glucose during the exercise, your type of the diet means low carbohydrate doesn't matter before the exercise. This graph shows that this is important. And this is the oxidation rate of the glucose. There is up to say 120 gram per hour. Muscle can take up to say 5 times the resting level during the heavy aerobic exercise. but liver can also produce up to 10 times during the intense exercise. So all the based upon all these things, small range of the glucose during the your blood sugar, blood in your blood circulation, only a small amount of intake is required. Because see, this is the performance effect, this is the amount of the glucose effect. It doesn't matter. There is no relationship. Haphazard relation is there. That means you don't have to take too much of glucose during the exercise. It doesn't matter. So a small amount of glucose intake is sufficient to prevent the hypoglycemia. Approximately around 20 to 25 gram per hour or so of the during the exercise is important. And therefore, intake of the glucose will reduce the amount of the insulin, and insulin reduction means you will be able to utilize fat, and fat utilization, increasing fat utilization, fat adaptation is important because your body has more storage of fat, and therefore the store fat could fail running for nearly 4 days, but muscle glycogen only for less than 2 hours. Therefore, the secret of endurance training lies in unlocking the potential to use fat and becoming fat adaptation. This one has to understand. So these are the concepts of this thing, and therefore a constant monitoring of the exercise induced whether exercise induced hypoglycemia is there or not by using CGM is important. And also RER monitoring is also important if you have the equipment, because if resting RER is less, that means your body is adapted you to utilize more fat. In such an individual, high fat will be more successful, can be more successful. So this thing, these are a practical point one has to understand. And what is the possibility? The possibility shows that the different paper has now come up with shows that at least for endurance exercise performance is similar for low carb and high carb diet, and your athlete body has a capacity to adapt to different type of diet, and not necessarily high carb diet is always beneficial for performance, and they may be they may be associated with, say, non-alcoholic fatty liver or metabolic associated fatty liver disease or type 2 diabetes, insulin resistant, obesity, so type 3 diabetic, Alzheimer, all these things, or different hypertension, different type of thing. And because of that, a personalized nutrition plan should be done, and CGM, continuous use of the glucose monitoring, is more important. And one has to understand, and performance always multifactorial. It's not one a particular diet is not responsible. There are lots of things is there. So a personalized individualization of nutrition, perhaps periodization can be also done. Like for example, train high, that is train high and sleep low. So if you in a resting condition, you may take low carb diet, but in case of the heavy exercise, say you may take some amount of the carbohydrate depending upon a requirement, individual carbohydrate tolerance, or say in order to prevent REDS, relative energy deficiency in sports, you can take a small amount of carbohydrates utilized during the exercise in order to prevent the deficiency. You don't have to take too much fat adaptation. So glycemia is the most important factor, and hence liver glycogen is more important. Your mind should be open to the latest research and evidence. It's challenging your earlier reading, earlier belief. You must be ready to accept, depending upon the requirement. That's why positive activity, exercise, and lifestyle is more important, because it will lead to the positive physiology, which include the right amount of the nutrition. Health can be maintained, and hence high carb diet and low carb diet, all these things one has to understand, and one has to see that your body has a more adipocyte tissue. You have to somehow use this high amount of the energy in your body. You don't have to take excessive amount of the type fuel during the exercise. You don't have to depend from external. If you are able to use what is there, your internal, so minimum amount of the external, more depend upon your already stored energy in the form of the fat. And these of the lifestyle, chronic non-communicable, these in the form of insulin resistance, and all that thing which may happen because of the high carb diet, high omega 6 fatty acid intake, high processed food intake, all these things be bought on performance and long-term health by following a proper nutrition. Thank you very much.